Question mark, question mark?
Like just keep.
All right, yesterday we started talking about confidence. Last couple of days we talked about confidence intervals. I had a worksheet last night in regards to confidence interval. Once again, what we are trying to deal with and what we're trying to work with is we're trying to use a sample to estimate a population, an interval in regards to the population, what a value will be within the population. We talked about the presidential elections the other day. We want to get a good guesstimate. We want to have a talking point. And with statisticians, that's what they mainly want, is they want numbers that they can work with. They may or may not be true, but they want to be able to have points that are there so they can make decisions. When dealing with our confidence interval, and when you're dealing with your confidence interval, we have our sample mean, we have plus or minus our z-score for that confidence interval, we have our standard deviation divided by the square root of n. And once again, the standard deviation here, if we don't know the population, we can use our sample standard deviation. Now, if we take a look at problem number 3 on the homework, you have a study of 35 golfers showed their average score in a particular golf course was a 92. Standard deviation was a sample was 5. So you have 35 golfers, 35 golfers, and they took the average of their score for 18 holes. Hopefully it's 18 holes and not 9 holes, right, Thad?
Yeah.
And the sample for 18 holes for them was a 92. And their standard deviation was a value of 5. And what we want is we want to determine a confidence interval for what would be the population score, because all we are dealing with here is we're dealing with 35 scores. But there's more than 35 golfers that are out there. So on average, what would be the population average given this data? Well, in part number 1, the question I ask you is, what is the best point estimate for the mean? Well, now we have to go back and refer to the idea of a point estimate. In our notes, what was our best point estimate? What is the best point estimate from our notes? What mean? The sample mean. The sample mean is your best point estimate. Well, what is given up here is the sample mean. So the best point estimate is this value of 92. That's your best point estimate. Now, what I ask you to do is calculate a confidence interval 90, 95, 99. We're just dealing with a 99% confidence interval in this one. So if we're dealing with a 99% confidence interval, we can look at our table to see what is the z-score for that confidence interval. Okay. Once again, what we could do, what we did initially after this, is we did a bell-shaped curve. With a bell-shaped curve, we put our 0 in there. We put areas on both sides of that 0 value, and then looked at the body of our z-table to find what is the z-score. But that's a lot of work to do each and every time, especially when we're dealing with mainly the same confidence intervals, 90, 95, and 99% confidence interval. So we have a table that we went through in the notes yesterday, the last couple of days. And today I'll give you another table. You'll be able to find this value a lot easier. Our z value for the confidence interval for 99% is what? Yeah. Table, the bottom of the table. Left-hand side. 2.58. Okay, 2.58. Okay, if we look at our table, We get a value of 2.58 from our table. So we can then find our confidence interval. Our population mean will be somewhere in between this x bar plus the z for the confidence interval times the standard deviation divided by square root of n, and this x bar, our sample mean, minus our z for the confidence interval times the standard deviation divided by the square root of n. So now it's a matter of just plugging in our values. Okay, we put in our sample mean, our z for is 2.58, standard deviation 5, square root of n is 35, and it turns into a clickety-clack exercise. If you haven't done it, please do, and check your answer with somebody around you. Once again, rounding in statistics. Go one more than your data value. Our data value is a 92. So you go one more decimal place, go to the nearest 10 with our data value. May, what do you have for your two values?
89.8.
89.8 and what?
94.2.
94.2. All right. When we deal with statistics, the main thing is to, the clickety-clack through the calculator, the mathematics is not very difficult. But the understanding of the meaning behind this is what needs to be written out. So at this point, this here, once again, is the population mean. We are 99% confident the population mean for golf scores at this course is between 89.2 and 94 or 89.8. And 94.2. And that's what we're dealing with respect to a guesstimate. Just to rehash, this here is your error. This value here is your error that you're adding or subtracting to your sample mean. Sample mean is what we gather, then we have our error, one side or another. But once again, the understanding of what is happening here and writing it out is the important part of statistics from here on out. We're 99% confident, which means if you're 99% confident in something occurring, you feel pretty good about that. Okay? You feel pretty good, given the data that we have. Questions you have? All right, today, we have two things here. The sample that we use up till now. We talked about the law of large numbers and working with the law of large numbers. We want a sample that is greater than 30 to be able to deal with our calculations. That's the idea of law of large numbers, and the idea of trying to get things normal. We want to try to get things normal. To get things normal, we like to have a sample size that is greater than 30 to get things in a normal sense. And if we get things in a normal sense, we can use our z-table and we can use all of our data values. The problem you have run into is sometimes you may not have a sample of 30. You may only have a sample of 20. You may only have a sample of 15. Well, as statisticians and statisticians, they still want to be able to make predictions. They still want to be able to predict out. So how do we deal with this when the sample size isn't quite 30, which means we may not quite have normalcy. The law of large numbers may not help us out very well. Well, we deal with this in regards to working through what is called a t-distribution. Okay, which is we have a z-table I gave you. We now have a t-table that we're going to start utilizing a lot more. When you deal with a t-distribution, it is utilized when your sample size is smaller than 30. When your sample size is smaller than 30, we still want to be able to make predictions. We still want to be able to make those predictions out. But the sample size is not quite there. But it's okay. We're statisticians. Statisticians, they want numbers to work with. We still want to be able to approximate a mean with some sort of confidence. So we use what is called a t-distribution. Things that we maintain, that we carry over from a normal bell-shaped t-distribution or z-distribution, is you're still going to be dealing with a bell-shaped curve. You're still dealing with a bell-shaped curve. You're still going to be symmetric about the mean. Those things are maintained. The mean, median, mode are still 0, theoretically 0. We're still standardizing the idea, the z-score, standardizing the idea. Mean, median, mode still 0, located in the center of the distribution when we standardize it. And the curve never touches the x-axis. You're still asymptotic. We still have a bell-shaped curve. Everything that we have dealt with up till now, we're still dealing with. But since we have a smaller number, we have some uniqueness to the t-distribution. And this will be, once again, I'm going to ask you questions on the next quiz. It's going to be, give me some characteristics that's unique to the t-distribution. Okay, these are z-distribution ideas right here. These are things in normal bell-shaped curve we've already dealt with. What's unique? Your variance will now be greater than 1, which means your standard deviation is going to be greater than 1. Your variance is now going to be greater than 1. When we normalize back to our characteristics of a normal distribution, going back to what we had in the last section, we did a normal distribution. The mean, when we standardize our scores, the mean was, do we remember? 0, and the standard deviation was 1. Okay? Mean was 0, standard deviation 1. That was our normal distribution. When we start talking about t-distribution, your variance is now greater than 1, which means your standard deviation is going to be greater than 1. The t-distribution is a family of bell-shaped curves based on the degree of freedom. Not bad. The degree of freedom, which is based on your sample size. So we now have another value that we had to calculate. It's called the degree of freedom. And that's based on the sample size. The last thing, as the sample size increases, once again, law of large numbers. Law of large numbers. The t-distribution will approach a standard normal distribution, a z bell-shaped curve. Once again, that law of large numbers continues to rehash itself again. The bigger the sample, the better off we are with our statistical values. We just don't. If you think about testing pharmaceutical drugs to cure something, you just don't give it to one person and say that one person's going to reflect the entire population. You have to do a lot of people to reflect what the population would be for an experimental drug. Okay, here comes probably the most difficult mathematical thing that we will do in this class, is to calculate the degree of freedom. Just be ready. How we calculate the degree of freedom is we take our sample size, n, and we subtract 1 from it.
Oh
Whew, man, that's going to tax me. We take our sample size and we subtract 1 from it. That gives us our degree of freedom.
You scared me.
We still want to estimate population mean. Population mean. How this changes from what we just did is we still have our sample mean. That should be a sample mean. Give me a bar here. We have our sample mean plus a t-value for the confidence interval times the standard deviation divided by the square root of n, and our sample mean plus our t-value for the confidence interval times the standard deviation divided by square root of n. It is the exact same formula as what you just dealt with, except for the z for the confidence interval is replaced with the t for the confidence interval, which now goes to our t-table. We use 3 values, 1.65, 1.96, and 2.58 for the z values. Now this t for the confidence interval is going to change. What occurs? This is a family of bell-shaped curves. Okay, we have a family of bell-shaped curves. What we had to begin with we have our normal z curve. we still have our 0 here. Okay, that's what we've dealt with up till now. Now, when we start dealing with the family of curves and the t-scores, and the t family of curves, what you can think will happen is if you would take two hands and squish from the two sides. Well, when you squish from the two sides, what's going to happen to the top?
It's gonna go up.
It's going to go up. So what happens here is we start to get a family of curves
Ooh.
where Sally's hump on the camel starts going up. So we have Sally and the camel has just only one hump. Okay, that one hump just starts getting higher. We start squishing the sides here. This happens when the n, or the sample size, gets smaller. As the sample size gets smaller, Sally and the camel's hump gets higher. Okay? As n gets bigger, we get closer to our bell-shaped curve. So we have a family of curves here. The family of curves, which is illustrated by, once again, our t-table here. On the t-table, what you have along the left-hand side of the t-table, you have the column that says DF. What does that stand for? What do you think? DF.
I have no idea.
Huh? Degree of freedom.
I get it.
DF.
Yeah.
Okay, so we have a degree of freedom. Now, what's nice about the t-table is if you look along the top here, if you look along the top, the first row along the top, it says confidence interval. So you look at your confidence interval, and you'll have to take it down to a degree of freedom. Now, the degree of freedoms only go down to 28. Okay, which means 29 and 30 are going to be gone. Because when we get to that point, we're close enough to get to a z-table. So we can use our z-value. Well, if we look at the very bottom row of the t-table, it goes degree of freedom down to 28, then it has z, which means your sample size is getting bigger, which means the degree of freedom is getting bigger, which gives us the z-values along the bottom. So your z-values can come off the bottom, your t-table values come off here. Study of 25 students show that they spend an average of $18.53. This is no problem, obviously, because now we only get about a quarter of a tank with this. $18.53 of gasoline per week.
That'd be nice.
Yeah, that would be. Oh, back when I was your age, I went down the gas station with a $5 bill. Fill her up. $5 bill.
Dang.
Yeah. It was 30, 40 cents a gallon. 10-gallon tank, 30, 40 cents a gallon. That was $4. Oh, it was nice. But I also worked at a pool, I worked at a pool, and my wage per hour, I looked at my number of hours that I worked a week, and I just multiplied by 2 because I got $2 an hour. So if I worked 25 hours that week, I got $50.
Oh my.
Then they take taxes off, anyways.
Hey, like.
So we have a sample of N25 students. Show the average cost. So we have our sample mean of $18.53 per week. Standard deviation of $3. We want to have a 90% confidence interval for the true mean, or the population mean. If the sample size is 25, degree of freedom would be what, Sam?
24.
24, here we go. 25 minus 1, 24. We want the population mean. Okay, we want a guesstimate for the population mean. So we have sample mean minus t for the confidence interval, standard deviation, square root of n, and sample mean plus t for the confidence interval, standard deviation divided by the square root of n. Well, let's take a look at this. We have a degree of freedom of 24 and a 90% confidence interval. So let's look at our table. We go across the top to 90% confidence interval. Across the top to 90% confidence interval, and then we drop down to 24. Or if you want to go down to 24 first and then come across to the 90% one, that's up to you. So if I go 24, 90% confidence interval, our table value is what value here?
1.711.
1.711. Anybody not be able to find that? Okay, degree of freedom, confidence interval. So now we just plug in. So we have 1853 minus 1.711 times standard deviation 3, square root of 25, and then we have the plus of that. So find the value and then write yourself a statement. Find your two values and then write yourself a statement. Once again, that's the biggest part of what we're doing here, because mathematically, this is not going to ooh and ah anybody. There's not anybody here that should be saying, ooh, ouch, I'm not quite sure about this. And how to enter it into your calculator. And what's two values you come up with?
17.690.
You have another decimal point there? Because we're dollars and cents. 60 and 1960.
Wait.
Oh my.
We're talking about dollars and cents here.
Oh, then never mind. 19.56.
19.56. And the 18, and what's this one? Are we good with this one? $17.60. We good with that?
It should be 5, 6.
Huh?
Oh wait, 17. I got 0.5034. Yeah. I got 17.50. Yeah.
We good with that?
Yeah,
50?
that.
All right. All right, now we go with the numbers.
Oh yeah.
All right, then we are 90% confident. Let's see, population mean for college, or for gas bought. Is between our two values here. I want you to take a look at very quickly. Problem number 3. Problem number 3 in the homework. Problem number 3 in the homework. I give you a set of data. I don't give you the sample mean or standard deviation. I just give you data. What you need to do is calculate the mean standard deviation. Well, we've done that, been there, done that beginning of the year. What your calculator will do for you. Okay? What your calculator will do for you. If you hit your stat button, which is above your program, below your delete, hit your stat button, you should come up with this right here. If you go to edit, you should get 2 lists. You should get a bunch of lists there. Alright? What you can do is enter in your data values. So enter in 112, hit enter. 120, enter. 98, enter. 55, enter. 71, enter, and so on. Okay, I'm going to stop there because we're running out of time. What your calculator will do for you is now if you hit your stat button again, hit your stat button, go to the second option, hit your right arrow, calculate. One variable statistics, it gives you the mean and also the standard deviation. And you don't have to do the calculations. Adios, have a good weekend.